Welcome to the APL quest. See APL Wiki for details. Today's task is the fourth from the 2015 round of the APL problem solving competition. We are to implement what's traditionally called Progressive Dyadic Iota or Progressive Index of. It's just like normal index of, but instead of finding the first occurrence of every element on the right in the array on the left, it consumes the elements on the left. So it's like without replacement, index of without replacement. And this is a classic problem in APL, and it has been discussed and documented for decades. The most commonly used traditional formulation for this is very well explained in the APL cultivations, and there's also a link there to a video where I explain this. So I'm not going to spend too much time and energy on this, just to show that it works and how we can update the traditional formulation to the modern times. Let's have some sample data. We got Landon and Finnegan, and our task is then to find the indices without replacement. So F isn't found, and there are 6 elements in Landon, which means that it should get B index 7, because that's how iota works. Same thing goes for I. N finds its match in position 3, but that means this N is consumed, and the second N has to go all the way to element 6. E and G are not found, so they're going to be 7 as well. A goes to the A in Landon, and the final N, while there are N's in Landon, both of them have now been consumed by the previous N's, and it will be as if there are no more N's, and we also get a 7. So the traditional formulation in question, it goes like this. And if we try it on the arguments, oops, made a mistake here. Oh, yes, it has, they're missing an iota, no, another iota, and a reshape here. Okay. Then we get these results as we said. 7, 7 for the F and I. 3 and 6, those are the first two N's consuming the 2 N's in London. 7, 7, the E and G. 2 is the A, and 7 is the final N, which cannot find its match because the 2 N's have already been consumed. And this all works very nicely. However, if we change our arguments into matrices by applying table to both of them, then we get an error. And this is because this traditional formulation is using trailing axes and other inappropriate functions for such a thing. But we can quite easily update it to handle such cases. The problem here is we're concatenating the wrong way. We want to add more major cells, so we need to concatenate first. And then we are taking indices here from this vector of indices, but this uses the shape of the right argument, and we only want the number of major cells from the arguments. And that solves our problem for higher rank arrays. Now we can notice some symmetry here. It looks almost identical what we have on the right and on the left of the middle iota. And so we could express this in terms of a single function that with slight modification becomes the same or the equivalent for these two sides. The only difference here is that we have swapped arguments on the concatenation, and then we switch which argument is being used for the tally. So let's express it like this. We have the right argument, and the left argument, and the right argument. We want to do this pre-processing on both arguments, but that doesn't work because it's not exactly the same function. So instead, we're going to make it into a train, and the train is we're going to create a function on the right, which we are then going to use in commuted form on the left. That commuting takes care of flipping the arguments of the concatenation here. But this one's already backwards. It's right argument on left, left argument on the right. So we commute it here, and it's going to be commuted right back again when we apply R over here. Then we have two grades that are monetic, so we apply those with the tops. And then we want the tally of the right argument. And then, of course, when we flip the arguments, it's going to be a tally of the left argument, which is exactly what we want here on the left side of the omega. So this is our solution, a somewhat shorter modern solution. So this is the modernized fin APL solution. Let's call that F. There's also an alternative formulation listed in the fin APL's idiom list, which is much the same. And if you go through the explanations for this one, then you will probably be able to go to have a look at this one and reason about why it's the equivalent. So I'm not going to explain that one in detail here either. It goes like this. And then we have something very similar to what we have here on the left, which we're going to put on the right. But we have the right argument indices being generated over here and swapped arguments of the concatenation over here. This alpha stays constant. It's always the left argument. I mean, let's try this. The basic principle here is that we are using the left argument as a constant lookup, so that the indices that we are generating for the cells are corresponding to each other, and then we're pairing them up. So we have unique identities for the indices in each array being paired up. Gives us the same result. And just as before, it doesn't work on high rank arrays, and just as before, we can fix this by replacing shape with tally, and last axis concatenation with first axis concatenation. And just as before, we can get rid of this this repetition of very similar code by using the reversed function from the right. The function on the right is we have to make it fit into the syntax of a train here. So here we have the tally of the right argument, and that's going to be the left argument when we are on the left, as we want up here. And then we want the indices of that, so we use another top. And here we have the backwards concatenation, do the swap there, look up into the constant, that's an AGH train, and then we have a top with grade over here. Some people, and I myself included, prefer not to have too many parentheses and too many nested levels of parentheses. And by observing that we have a single, though derived function on the right here of the iota, and a function that is a 4 train on the left, so there's an AGH3 train with another train that's a 4 train on the left, then we can see that if we swap the arguments of this middle iota, we get a single function derived on the left, and that doesn't need parenthesization, and we can avoid the parentheses here as well. So let's swap that over. Remember to commute the arguments of iota and put this 4 train in. Problem is, of course, that this is a monetic function, so we can pre-process the right argument of the middle iota commute with that. Another way we could do it would be to do a post-processing of the result of iota. But I like the other style a little bit more, because this iota is going to use this argument, and the grade at top is just in the way. It just separates the function here from its arguments. So we find it easier to read like this, and that works as well. And we can, well, if the other one is f, let's call this one g. We can even do a performance comparison between these two. Let's generate some test data. So alphabet, let's take 100 letters from here, or yeah, let's do 1,000 for now, to see a proper effect. And we do that, make a write argument, which is another random 1,000 letters there, and then we can copy in the CMPX from the defense workspace and run the two against each other. Well, in this case, F was significantly faster than G, and I've tried all kinds of cases. Turns out that in general, F is either somewhat or significantly faster. So that's the one I would recommend using. Okay, with that practical thing aside, let's look at some other approaches to this that I'll then explain fully. One way to go about this is to start with a comparison table between these two names. So here we have one row for every letter of Landon and one column for every letter of Finnegan. Let's turn this on its side. One way we can do that is by just putting in a def and flipping the arguments alpha and omega. So alpha is on the right and omega is on the left. What's the significance of this table? Well, it maybe becomes a little bit easier to see if we stick Landon on top and we stick Finnegan on the left. We just have to make sure that we add another element which is going to go up here in this corner where they meet. So just put a blank there. So what's happening here is that Finnegan has the letters that need to be given positions in Landon. And these vectors here, they represent kind of an identity for the letters in Finnegan in relation to the letters in Landon. So this is saying F in Finnegan does not find any match anywhere in Landon, and so too I. And that's right, because both F and I are going to eventually get a 7, not found. The ends identify with these two ends here. These are the ends that they want to consume, and they both want that. So they're going to get eventually distributed. These two ends here need to be distributed to these two ends. Then E and G are just like F and I. A will take one of the A's, of which there's only one. And then we have another N here down here, which is a contender for the A's, for the N's in Landon. But it's not going to get any because they're going to be consumed by the first two N's. Okay. So we want to put all the N's together, and we want to put all the letters together that are not matched, so that we can start matching up the available letters with the ones that are looking for them. And for this kind of grouping, that's where key comes into the picture. So let's just do a simple application of key, just to see what are the arguments to the operand for key. Oh, we're missing an A on the left. Here we go. So these are the unique rows. So this row is the not found row. This is the N row. This is the A row. And there are 4 letters. The letters in positions 1, 2, 5, and 6 that are of the not found type. And then there are 3 letters in position 3, 4, and 8 that are of the type where this mask indicates the letters that they can consume in Landon. For now, we're not so interested in the mask, but we want to know where are those letters and how many of them are there. So let's replace the alpha with the where of alpha. This gives us the indices that will need to be distributed. So these are the letters in Finnegan that are asking for these letters in London. These are the letters in Finnegan that are asking for, well, there aren't any, these letters in London, etc. Let's move things around a little bit and look at the count, because we need to see how many there are and if there are enough. So we can still put omega here, and this table here says that there are 4, that's the count of these, there are 4 letters that need to consume these letters over here. There are 3 letters that need to consume these. There is 1 letter that needs to consume these. And so we can use take here to take as many elements as we need. Those are the ones that are corresponding. Now when we do that, then we don't have enough, we're padding with zeros. So this indicates that 3, the third letter in Finnegan, is going to get the index 3. The 4th letter in Finnegan is going to get index 6. That's the last N in London. And the 8th letter in Finnegan, which is another N, won't be matched. So we can already kind of see our solution. The result here is already in here, all the information for it. Let's make it a little bit easier to access. So what we're going to do is we're going to take and pair up. So this 1 corresponds to this 0, and this 2 corresponds to this 0 over here. If we make what we have on the right here into a matrix, a 1-column matrix, and concatenate it to what's on the left, then we get a 2-column matrix. If we just do it like this, then key is going to pad with lots of elements because they're not the same shape. So let's enclose it just so we can see what it is we're doing. So here we can see that element 1 gets not found, element 2 gets not found, element 3 gets a 3, element 4 gets a 4, element 5 gets not found. So we need to combine these tables, and then we need to just put them in the correct order. Combining them we can do by concatenating them along the first axis. That's going to also enclose them, so we disclose them. And now we have all the information that we need. We just need to put it in the right order. We need to sort it by the first column. So let's do that. We could do the first column sort. We can also just sort by the whole table, because it doesn't matter when the first column are all unique elements. We're never going to look at the second column at all. Now they're in the right order, and here's our result actually. Just we need to adjust these zeros to 7s eventually, and we don't actually need the left column either. We just needed it for the sorting. So this means we're getting all the columns. We just want column 2. And then we need to transform all our zeros into 7s. So 7 meaning 1 beyond the last element position in the left argument. So 1 beyond the length of the left argument replaces the values at those values where they are where 0 equals them, and that gives us our solution. Now there is an additional problem, that is again high rank comes to haunt us a bit. Right, what's happening here? Things are going very wrong, and this would also happen if our arrays were nested, and that is because we're using a scalar function equality here. This tries to compare all the elements rather than compare the individual major cells. And not only that, if they were nested, it would also dig in and create a nested structure of booleans, assuming the length would be matching everywhere, and this could even error. So we need to write this outer product, but in terms of match, and we can do that. So what we want is we want every major cell from omega here needs to be compared to all the major cells from alpha. And so we can pair up first the major cells from omega, so that's rank -1, with the entire alpha. So we give it 99 as a big value that's bigger than the rank of alpha. So now what match would see is, in our case, a row on the left and an entire matrix on the right. And now it needs to again traverse that and compare the major cells. So on the right need to be paired up with the entire one cell, which is a corresponding cell on the left. And then we get our proper result. So let's call this K for key, because it's the key-based approach. The key is doing the heavy lifting here. Okay, a final approach to this. It's not going to be an APL approach, but it's a different way of expressing the way we might think about this problem. And for this, let's use Landon as a left argument, but I'm also going to use a different argument, which is just going to be NaN for now, and then we'll expand on that later. So NaN, the first n consumes here, that becomes a 3, then we should get a 2, and then we should get a 6 at the end. We can confirm that. We can try that with K that we've just defined. So 3, 2, 6. Right. What we're going to do is we are going to literally go through and consume letters the way we've been talking about it. Now, we are not allowed to change anything in the left argument of a defin. So let's make instead a copy of it that we are allowed to change in whichever way. We'll call that A, because it's like alpha. And now that that's initialized, we're going to traverse all the elements in the right side. And for each of them, we're going to consume an element of A. What does that mean, consume? Well, let's change it into something that won't match. So the first n in Landon, which if you change that into something that's not an n, then when we get around to the second n in Nan, it won't match that n anymore, and we'll have to go to the second one. So then it has been consumed. And how do we find which element to consume? Well, we can just look up the element, the first match, because once we have consumed it, it won't be a match anymore. And then we change that into some kind of symbol that indicates that it's been consumed. This is an assignment, so everything here is going to be very quiet, but we can discard these assignments. Every assignment here is going to result in this symbol, so that's not very interesting. Instead, we discard that, and instead we return this modified array A. And we can see that the A and the N and the N have been consumed. We can even look at what exactly is going on every time around the loop by printing this current state of A before it gets updated. And here we can see the evolution. First we've got the pristine Landon, and then we're consuming an N, consuming an A, and consuming the final N. However, we're not actually interested in what Landon looks like when it's being consumed. We're interested in the indices instead. And indices, well, they're the ones right here, so we can print that instead. And we can see that we're getting our 3, 2, and 6, and then these are the ones that are being consumed. Now, we don't want to print them, we want to return them, so let's give them a name. And then every time around the loop here, we have a new value for I, so we let the function return that instead. And those are the values that we want, so we don't need our A being printed at the end anymore. And that gives us our result. But there are some issues that we're going to fix. What happens if I add an element here that's not found? We get an index error. The reason is because already this lookup, we're going to get and not found, which is one element beyond, which is one index beyond the last index, and one index beyond the last index is not a valid index for A. What can we do about that? Well, we can create a new position in A, which is like a sacrificial position. We're going to override it whenever we need to override something that's not in A. So let's just add one more element. We can use the same symbol for that, doesn't matter. It's probably going to be overwritten anyway. And then when we look up here, we have to watch out because now A has one more element and we'll get an index that's too large. So we'll drop that before we do the lookup. You can see that S got a 7 as it should. Further complications. Well, what happens if this element that we have chosen as our sacrificial element or a marker for something having been consumed? What happens if that itself appears in the array? That does not look right. What's happening? We remember how when we are consuming things, we overwrite that element with the special symbol. And so by the time we have consumed n and a and n, our lambda looks like this. Now we come and look for that same element, and we're going to find that in this position too. So we need a value that's not going to match itself at all. And here's a special trick, a kind of nasty one. A namespace, we can create a new namespace. And though a namespace is equal to itself, even two namespaces that are created under the same circumstances and are otherwise identical with regards to their content, they are passed around in APL by reference and they have an identity, so they don't match each other. This means that we can use namespaces that are being generated. We will make a new namespace. We could make a new namespace every time, and then we ensure that this namespace that we are generating here will never appear in any array, because every namespace has its own identity, and this one has never existed before. We could actually also just use a single namespace as the namespace that we're blooding out with, but this itself would work. If you wanted to use a single one, then we could define it outside and say put it here. We can use that here as well. It doesn't matter because that we have it in the lookup array, because we never have any array coming in where we want to look for this namespace, because the namespace doesn't exist yet. We're only creating it once here. So this would work as well. And then, as the everlasting trouble, it would be a problem if we had high rank arrays. There are multiple problems here, and with the first problem we're hitting, apparently, but there's actually something going on before that, is the lookup. And the problem is that we're consuming elements one by one rather than going major cell by major cell. So we should change this into a rank -1 over here. Another issue is that we're concatenating the wrong way. We should add another major cell, which will then be filled with this element. And finally, we're doing indexing over here with square brackets, which isn't general. We can't index into a general array using a single call with square brackets, because we would potentially need trailing semicolons over here, and that doesn't work. So we'll change it into using the index function instead. Right here, like that. And now we're getting the result we want, using high rank arrays as well. So let's call this n for using the namespace. And if we look at these solutions, we found that F was the fastest ones of F and G, and we had the one that was based on key, and then we have the one that uses namespaces. This over here was an outer product, and that's going to be problematic for very large data. Let's say that both arguments have 1,000 elements. That gives us a million elements, a million comparisons there. So that's going to be very inefficient. So we should change our test cases to something smaller. Let's just do 100 then. And a new y as well. And then we can compare them all. So we have x, f, y, and x, k, y, and x, n, y. And, well, it's very clear that the right way is the old way. So when you want to do this kind of allocation, which can be used, for example, to fulfill orders from a warehouse with a limited amount on a first come first served basis, or allocate seats in an airplane with various classes of seats, then use the modernized expression from the Fin APL idiom list. And for the full explanation of that, have a look at the links in the description for the video. Thank you for watching.